In this case, there is really one easy way to do it and one hard way to do it. If you look at the machine, you're really in trouble. Reversing these push-down machines are really hard. You've got to reverse the stack operations and turn the arrows around. I remember when we reversed them, sometimes non-determinism occurs. It was a big mess even for finite state machines. To do it with push-down machines, it's really a mess. So how do you do it with grammars? You can just take the right sides of all the productions and turn them around. Then anything that you used to generate before generates the same way, except it ends up reversed. It generates exactly the reverse of the original language. Just take all the productions and turn them around. Look at them through the other side of the blackboard. So context-free languages are closed under reversal. There's a few of these other sets like min and max and cycle that I talked about for finite state machines. Regular sets, they're closed under all of them. Context-free languages happen to be closed under cycle, but not under min and max. Deterministic context-free languages are closed under min and max. I won't talk about the details there. They're not so obvious, but they're not impossibly hard either. They're things to think about. More importantly, deterministic context-free languages are closed under complement, but not under union. More or less, the proof that deterministic context-free languages are closed under complement is that toggle final, non-final states proof. There's some technicalities, but it's more or less that simple proof. You can't toggle non-deterministic machines and get the complement. It doesn't work. But you can toggle deterministic machines and get the complement. How come deterministic context-free languages are not closed under union? It's because if you do that same e-move trick, you get non-determinism. And if you do the grammar trick, where the new start symbol goes to S and to T, that turns out to be a grammar that's not of an LRK form. So there's no way to obviously union deterministic context-free languages together, and in fact they're not closed under union. In fact, here are two deterministic context-free languages, and if I union them together, I get a provably non-deterministic context-free language. There's no deterministic language that gets their union. So definitely not closed under union. Context-free languages are closed under concatenation. How do you prove that? Okay, you can do that e-move from the except of 1 to the... But doesn't that make it non-deterministic? I guess it's okay. It's non-deterministic. What about the grammars? Can you do it with a grammar? You have two start symbols for two grammars, S and T. Make a new start symbol that goes to S, T. So you can do it with grammars too. What about star? Is it closed under star?
Yes.
How? How do you show that it's closed under star? Because it says so. If I have a grammar, S, context-free grammar, generates a lot of stuff. How do I make a new grammar that generates any repetition of any string here? I'm not sure that would give me everything.
A new start state that goes to S or SS.
So a new start state, S new, that goes to...
S or...
What about this? What does this do? Or epsilon. What does this do? S new goes to S, S new. It's a Dr. Seuss thing. What's new? SNU goes to SS new. You go ahead and do this once, and you get SSS new. You do it again, you get SSS new. Sooner or later, S new is going to disappear. So this gives you as many copies of S as you want. And that's it. That's the proof.
You could just have S go to SS.
Yeah, right. I think that's okay too. Yes. What about DCFLs? Are they closed under concatenation or star? It's not at all obvious. Because for one thing, you can't do these tricks in grammars and expect them to stay LRK. And you can't go ahead and make e-moves from final states to new states.
Could you just clarify for grammars what DCFLs are?
I can't. It would take me an hour and a half.
Okay. Because it's clear from the machine point of perspective, but from the grammar's...
It is just not clear. It is, it's an hour and a half. An hour and a half of lots of details, examples, and not obvious. There is no simple way to look at a grammar and say, hey, that's an LRK grammar. There's a complicated way to look at it. Compute what's called the first sets. Compute the follow sets. Compute the list of legal items. It's a big procedure. And even when you do it many, many times, you have to really go through the details before you know the answer. Even when you're good at it and intuitive at it, it's rare to be able to glance and still have the right idea in advance without going through the details. So I keep just saying LRK, and it would be nice if I could give you the intuition, but we need to spend 2 or 3 recitations on it. And hopefully we will. Okay, so this tells you a little bit about closure problems. I'll get back to closure and decision algorithms in more detail tomorrow. I want to leave you with this one puzzle. And it's not just an arbitrary puzzle. It relates to undecidability. It's called the post-correspondence problem. You can read a lot about the post-correspondence problem in your text, in any of these texts that we have on reserve. And also, somebody was reading Gödel Escher Bach, I forget who, this month. That's a Pulitzer Prize-winning, I don't know what you want to call it, book. It's not a novel. It's just a weird book by what's it by? By Hofstadter, who's at Indiana, I think, and he did some AI and some theory. And anyway, he wrote this book from ideas in his early graduate days, and it's kind of a weaving of music, art, and theory of computation all into one, where the music is the fugues of Johann Sebastian Bach, and the art is mostly M.C. Escher, and the theory is mostly Kurt Gödel and all these things you're learning this month. In it, he talks about the post-correspondence problem in his very clever, interesting way. But let me just tell you what it is, because it's a cool problem. Somebody gives you 2 sets of strings. This is number 1, number 2, number 3. This is list A, list B. So there's 3 pairs here. In the general problem, somebody gives you any number of pairs. Here there's just 3 in the list. And the question is, can I make a sequence of these numbers? For example, 1, 1, 3, 2, 2, 1. Can I make a sequence of these numbers so that when I go ahead and concatenate all the strings from each list, A, B, in that order of that sequence, that I get the 2 strings to be the same? Let's try it in this example. 1, 1 means, let's do the A part. A would be 1, 0, 1, 0. 3 would be 1, 1, 0, 1, 1, 0. 2 2s would be 1, 1, 1, 1, 1, 1. And then another 1 would be 1, 0. And then for B, it would be 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 2 2, 0, 1, 0, 1, and then another 1, 1, 0, 1, 1, 0. Okay, so that's that particular sequence I came up with, generates this for A and for B. And the question is, are they the same? They're not the same. The question is there a sequence that makes them the same? The sequence you come up with can be arbitrarily long. Or can you look at it and convince me that there's no sequence that will ever work? Does everyone understand the problem or the puzzle? So given a set of pairs, can you do it or can't you? Can you come up with a sequence that makes these 2 strings even out, or can't you? In his book, he comes up with a very nice example, and I forget who's having the conversation in the example, the tortoise and the Achilles and who knows who. But the turtle and the Greek hero are having a conversation about this problem, and one of them convinces the other that there's no way to do it for the particular set of strings that they talk about. And it's a very clever argument. Something about the parity of the strings, that any sequence here has an odd number of ones, and any sequence here has an even number of ones, and